Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to have a review of sets and how it will be used in this course. So in this topic, we will define a set, we'll define a subset, we will define the term disjoint, and we will give examples of these, focusing on how they will be used in this course. So, a set is a collection of unique objects. Definition. For example, I could have the set of all nanotechnology engineering students in 1A. I could also have the set of all people taller than 3 meters. I don't think anyone's that tall, but I could have such a set. I could have the set of all 2-dimensionals r squared. I could also have a set of just 2 vectors shown here. Now, if we are listing just a finite number of items and we want to describe it as a collection of unique items, then we will just put them in parentheses and describe them as this set. So here I would have a set of 6 vectors with the general assumption that all 6 vectors are different. Now, all of these vectors are going to come from the same vector space. We're never going to mix up sets with vectors from R2 and R3 and R5 and continuous functions. That doesn't make sense in this course. Now, there is one special set. The set with no objects is denoted with an empty pair of curly braces. This is called the empty set. Now, initially, however, the only sets we're going to refer to are entire vector spaces as a set. So, for example, we will start with the vector space of all vectors in r to the 6. Each of them is unique, and that together forms a set. Another set is the set of all polynomials in x with real coefficients. And that is, as you'll recall from the last talk, denoted by bold R indexed with X. Now, sometimes we will describe sets through some sort of description. For example, the set of all 2-dimensional vectors where each entry has an absolute value of less than or equal to 1. Well, this is one such vector. So if you were to calculate the absolute value of each of these entries, you would see that the absolute value of each of these is less than 1. Here's a vector that's not in that set, specifically because the first entry, 0.6 plus 0.8j, actually has an absolute value exactly equal to 1. We could also describe a set through images. So, for example, given all the vectors in R2, I may describe the set of all points that appear on this line, including the origin. Alternatively, I may describe the set of all the points that fall into this cone that includes the boundaries and the origin. Now, I may use a description as follows. The set of all discrete signals that are bounded. That is, a discrete signal is bounded if the values in that signal never exceed in absolute value some fixed maximum. So, for example, a geometric sequence where the ratio is less than 1 in absolute value is always going to be less than or equal to 1. On the other hand, the sequence 0, 10 times sine of 1, 10 times sine of 2, 10 times sine of 3, and so on and so forth, also is going to be bounded because the maximum value that sine of x can take in absolute value is 1. So if the maximum we're multiplying sine of n by is 10, the maximum value that may ever possibly appear in this particular discrete signal is, in absolute value, is something equal to 10. Here, on the other hand, is a discrete signal that, assuming it continues to increase, is not bounded. So this is an example of a signal that would not fall into the set of all bounded signals, because this signal ultimately goes to infinity. Note that the zero vector for discrete signals is bounded, because given any positive value, all entries are less than that positive value in the zero signal, or the zero vector. Now, we may denote a set by an italicized capital Latin letter. So, for example, I may have the set S of all students at the University of Waterloo, the set T of all graduates from secondary schools in Ontario, the set U of all complex numbers that have an absolute value less than or equal to 1, and the set W of all three-dimensional vectors that have non-negative entries, meaning that all of the entries are either 0 or positive. If we are discussing an arbitrary vector space, where it could be the vector space of polynomials, or it could be 5-dimensional vectors or 3-dimensional vectors, it doesn't matter. We will describe such a vector space by a script, capital U or capital V, perhaps capital W. Now, given two real numbers alpha and beta, we may define a relationship alpha is less than or equal to beta, which may or may not be true for any two values. So 1 is less than or equal to 5, 7 is not less than or equal to 4. The relationship tells us how two values may be related to each other. So if alpha is less than or equal to beta, then alpha lies, or is either equal to beta or lies to the left of beta on the real line in the usual orientation. Now, definition. One set is said to be a subset of another set if every element in the first set is also in the second set. So S is a subset of T if every element in S is also in T. This is written using this notation, which looks sort of similar to that of less than or equal to. Now, for the real numbers, we're guaranteed that any two real numbers, either alpha is less than or equal to beta, or beta is less than or equal to alpha, or both. But at least one of the two must be true. This is not true for sets. For example, the set of all real numbers that are positive is not a subset of all real numbers on the interval from -1 to 1. Why? Because 7 is in the set of all positive real numbers, but it is not in the interval -1 to 1. On the other hand, the value, or the real number, -1/2 is in the set of all numbers on the interval from -1 to 1, but it is not in the set of all positive real numbers. So, in this case, the set of all positive real numbers is not a subset of all real numbers on the interval from -1 to 1, and all real numbers on the interval from -1 to 1 is not a subset of the positive real numbers. Now, some examples of subsets include, given the real numbers, all positive real numbers, all integers, and all integer multiples of 2 pi. Given all students at the University of Waterloo, all nanotechnology engineering students at Waterloo is a subset of all students. All students who pass this course is also going to be a subset of all students at Waterloo. Of course, at the current time, none of you have, but the assumption is, hopefully, all of you will. Here's another subset. Given the set of all students who graduated from Ontario secondary schools, all students here are not a subset of this larger set. Even though out of the 120 students in this course, there are students here who did not graduate from Ontario secondary schools. So the set of all students here is not a subset of all students who graduated from Ontario secondary schools. Now, in this course, we will always be speaking of subsets of a given vector space. We may then ask how two subsets are related. Generally, subsets will be described with some sort of formula. So, for example, I may state that I'd like to consider the subset of all linear combinations of these two vectors. So let alpha equal 1.7 and beta equal 2.5. Then 1.7 times the first vector plus 2.5 times the second vector is a linear combination of these two vectors. However, I'd like to consider all linear combinations of these two vectors. Similarly, I may describe a subset as all linear combinations of these two vectors. And then a question we may ask is, are these two subsets the same or are they different? Now, both must contain the 0 vector because 0 times one vector plus 0 times the second vector must equal the 0 vector. So the 0 vector must always be included in the collection or the subset of all linear combinations of any number of vectors. I may also have the set of all vectors of the form alpha plus 3, alpha minus 1, and alpha plus 1, where alpha is any real value. I may then ask, is this set containing just one vector? Is this a subset of the set I just described, or is it not? Now, given a set, any two subsets that have no points in common or no entries in common are going to be said to be disjoint. So, for example, given the real numbers, the irrational numbers are a subset and the integers are a subset. However, there's no irrational number that is an integer and there's no integer that is irrational by definition. Therefore, these two form disjoint subsets of the real numbers. Given a vector space script V, if two subsets both contain the 0 vector, then those two subsets are not going to be disjoint. So, following this topic, you understand the definition of a set, you understand the definition of subsets and disjoint subsets, and you have an idea as to how the concept of sets and subsets will be used in this class. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!